Hello and welcome to this introductory lecture on sound. Here we're going to talk about some characteristics of sound, just understanding that it's a longitudinal wave and so on. Then we're going to talk about energy and intensity of sound. Okay, so let's get right to it. So one of the first things that you might think about when it comes to sound is the idea of a decibel. This is kind of an everyday term that we use for describing sound. If you turn up a stereo, you're increasing the decibels. But what is a decibel? Well, it's a dimensionless quantity. It is represented in terms of units, if you will, but not truly units, because after all, it's dimensionless. But you can think of it almost like a radian, right? A counting tool. It's represented by the letters dB, which stands for decibel. All right. Now it's a measure of loudness, which is to say intensity, because loudness and intensity are synonyms. Okay. Now it relates to the actual physical quantity of intensity, although it's not equal in units to intensity, since after all, it doesn't have any units. In fact, it is a logarithmic scale that is based on a ratio of intensities. Okay. Now it's not a universal logarithmic scale at all. It is a logarithmic scale that is based on human perception at a particular value that has been measured for humans, right? So it's an anthropocentric type of measurement. Furthermore, the idea of having a logarithmic scale is really indicative of the fact that we're talking about a large range of intensities that the human ear can perceive. And when you have such a large range, many orders of magnitude, maybe 1 trillion difference between the weakest and the strongest sound that the human ear can pick up, it doesn't make sense to do it on a linear scale because the differences are just too large. Hence the idea of logarithms, it's more of a convenience. Okay, so one thing you're going to see then is this idea of the threshold of human hearing. And what this is it's used for comparison of sounds. It's how we actually compute and define the decibel. And it's equal to 10 to the negative 12 watts per square meter. And we call that I naught because that's the baseline intensity. That's the threshold intensity, okay? Because that's an intensity, okay? So that's the actual official definition, right? That we're stuck at, it's just exactly 10 to the negative 12, okay? Now, we've been talking a lot about intensity. We should officially define it. It's it is a physical quantity in its own right. It's represented by the letter I. That's really the kind of go-to variable for it. And what it is it's energy per time per area. So it's the joule per second per square meter. Another good way to think about it is it's the watt per square meter, because after all, the joule per second is a unit of power. And is measured in watts. Okay, so it's power per area. That's what intensity is. It makes a lot of sense for anything that's spreading out as a wave. We use it for earthquakes. We would use it for sound, because sound is spreading out as a wave. We use it for light as well. Okay, so absolutely when we talk about the light from other stars or from any source, then we absolutely use that same measurement, that idea of intensity. Okay, power per area. Now, one thing about phenomena like sound waves that spread out into space from a source, often considered just a very simple point source, well, that type of energy spread obeys the inverse square law. And this is a term that comes up a lot in physics because it is so prevalent. Now, the inverse square law is any physical quantity that decreases with the square of distance. The one we've seen is the gravitational force. Remember the universal gravitational law. There is a proportionality between that gravitational force and distance that was an inverse square. If we doubled the distance, we reduced the magnitude of the force by a factor of 1/4, okay? Because we square it, right? Inverse square. Well, it turns out that intensity obeys the inverse square law, okay? Now, the reason that the inverse square law is so ubiquitous, so common, is because of that idea of something spreading out freely into space. If I have a source, this could be a source of a sound, obviously, then that source is going to spread out, and it's going to spread out into consecutively larger circles. But really, if we think about it, they're not actually circles, they're spheres, right? And this is the energy spreading out. So there's just as much energy from conservation of energy, assuming you're losing no energy to any change, right? This is the mechanical energy of the sound wave is being perfectly conserved here, which is, obviously an idealization, right? There's no loss in anything else, but let's say it is. Well, then there's a fixed amount of energy, but that energy now is spread out over a bigger area. That means a reduction in intensity, okay? All right, it's like spraying a wall with a spray can of paint and finding out when you spray really close, you get a very thick layer of paint that runs, but as you go further and further away, that coverage on the wall is going to reduce with the square of the distance. It doesn't reduce linearly, it actually reduces with the square of the distance because it's related to area, even though there it actually is the area of a circle and not the surface area of a sphere in the case of the spray paint. All right? All right, so it's just such a common phenomenon, such a common relationship, the inverse square law. All right, so enough about our terms. Let's get right on to our key formulas. Okay, so we got a couple of them all about properties of sound. All right, and of course, look at inverse square law. So the first one is the speed of sound. So this is a helpful formula. Okay, now this is again pretty specific. It's not universal physics by any stretch of the imagination. This is really thinking about the properties of Earth's atmosphere, because it turns out that sound travels different in different materials. It has to do with the mechanical properties of that material. So different gases would carry sound differently. But in our own atmosphere, we have a particular kind of baseline speed, which is 331 meters per second. This is actually the speed of sound at 273 Kelvin. So this is speed of sound at, 0 degrees Celsius. Okay? So that's your 331. Now, a lot of times it's not that cold, so sound is going to be moving a bit faster. We often say 343 for room temperature, and it all comes from this formula right here. It's a nice formula because it's based off of Kelvin. That means we don't have to use one specific to Celsius. So we just get the velocity of sound in meters per second, and then you just plug in the temperature. Make sure you plug it in Kelvin. Take the square root of that ratio, whatever your temperature is, relative to 273, of course, equivalent to 0 Celsius, and there you go. You can find your sound. Now, obviously, what you're seeing here is that the speed of sound goes up, okay, with higher temperature, and it goes down with lower temperature. So the colder the air, the slower sound can move, okay? All right. Now, finally, our logarithmic relationship to define the decibel, okay? So the quasi-unit of the decibel is the dB. The variable that we tend to use is beta, right? So again, this is kind of the B being so prominent in the name of the decibel, okay? And after all, there is such thing as a bell, but no one ever uses them. We always use the decibel. Deci just means 10, so it's 10 bells, right, if you really want to be technical about it. And there indeed is the 10, and there's the log relationship, okay? So it's a log of a ratio. That ratio is dimensionless because it is a watt per square meter divided by a watt per square meter. There's that human hearing threshold right there, okay? That 10 to the negative 12 watts per square meter. And this is just the intensity that you're working with. Maybe you're solving for this and you're gonna have to work it outside of the log by raising both sides of the equation to the power of 10, or maybe you're just plugging it in and you're solving for a decibel value. We'll see examples of that. Now, one thing that's really neat is we can actually calculate this intensity using the inverse square law directly and with actual numbers. So we can think of the power of a certain source, okay? And then calculate the intensity with that power and 4 pi r squared. And if you recognize from geometry what 4 pi r squared is, it's the surface area of a sphere. So we're assuming here, there's no constraints, and this is sound that is spreading out, freely spreading out without any reflection or anything in 3 dimensions, okay? Now, we might be doing this in kind of situations, say, oh, we're going to be like further or closer to a speaker. You might say, oh, what about the reflected sound off of the floor? We're obviously ignoring those type of effects, right? For simplification, we're just taking sound to spread out freely in 3 dimensions, and we care about how much that energy is spread out over a particular surface, the gradually growing surface of the sphere as the energy of the sound wave just spreads, okay? And then finally, to kind of simplify, if we ever need to compare between 2 intensities and 2 ratios, then we can use this handy-dandy relationship to find the ratio of intensities and the ratio of distances, okay? Where the r is the radius from the wave source, okay? All right, so we'll get right to it and do some practice problems. Okay, so 2 types. Simple problems that involve the temperature-dependent velocity of sound. I just have one of those. And then problems that involve a point source of sound of a particular power and the intensity of that sound as a function of distance, all right? And it might be, the intensity, we might just be talking about it in terms of watts per square meter, or we might go ahead and convert it over to decibels. Because really that's the case, right? You can always talk about intensity in terms of watts per square meter. Sometimes though, we want to convert it to the decibels, again, just because of the large range of available intensities that the human ear can detect. Okay, so I color-coded the first one, and the rest aren't, but all but the first example are type 2. So let's do our 1 velocity of sound problem. You see a lightning strike in the distance and clearly see it ground, right, so hit the ground, on a large radio tower. Immediately after the strike, you use a stopwatch to measure the time until you hear the thunder and record very accurately 7.40 seconds. You then look up the distance to the radio tower and find it to be 2.57 kilometers away. Right? So you go online and find the distance. Based on this information, what must be the temperature of the air outside, right? So this is a very difficult and cumbersome way of measuring the temperature outside, okay? All right, so we're gonna go ahead and acknowledge that the velocity of sound, like any constant velocity, is just distance over time, and the velocity of sound is reasonably taken here as to be a constant. So we just have those 2,570 meters, just as the 2.57 kilometers, divided by the time it took to travel that distance, and we find a velocity of 347 meters per second. Okay, well, based on the fact that the velocity of sound is 331 meters per second at 0 degrees Celsius, we can figure that it's got to be not a cold day. So let's go ahead and find out what is the actual temperature. So here we'll just write our formula, and we're going to be solving for T. That's going to be our unknown. So we just go ahead and isolate T, okay, by just taking the ratio of the velocities and then squaring both sides, multiplying by 273 Kelvin, and we get 301 Kelvin, which is 27.5 degrees Celsius. So it's a warm, balmy day, okay? The kind of day you might expect a lightning storm. All right, so example 2. All right, so here we have a question all about power and intensity and so on. A person is shouting at the top of their lungs and emitting a 1 watt, all right, of energy, or 1 watt of energy, as sound waves. What is the loudness in decibels 1.5 meters from such a person? Okay, let's find out. All right, so to find the intensity, we use this formula here, okay? So then we have 1 watt, okay, because that's the actual power output, which is reasonable, by the way. The human larynx and so on can actually produce that much power. Those many joules per second. Here's our surface area of our sphere, 1.5 meters, so there we have it. We have 35 milliwatts per square meter, right? Not a lot of intensity, and that's actually true of a lot of sounds, right? So when we calculate our sounds, you may be surprised how small the actual intensity or even the power output is. That's kind of for a couple of reasons. First of all, it's not hard to produce sounds that the human ear can detect. We have quite sensitive ears. I mean, at least in the scheme of devices, right? I know not maybe compared to other mammals, but certainly they are relatively sensitive compared to maybe man-made machines. Furthermore, the idea is that we're completely simplifying it. This is sound without any loss, right? There's no turbulence in the air. There's no way for any of that sound energy to get lost. In reality, it's actually quite a lot of damping, right? But we don't cover damped sound. All right, so anyway, I just want to point that out because the values might be surprisingly small. Okay, so then we're going to go ahead and actually calculate the decibel. So it's really plug and chug at this point, right? We just use our formula, right? Remember that it's 10 times log because it's the decibel, right? And then there's the log, okay? We plugged in the intensity that we calculated for that given distance and that given power, and we find 105 decibels, okay? So that's our intensity, okay? Now, I call it an intensity. You can call it a loudness, right? You can call it, a dimensionless intensity ratio. It's all kind of interchangeable, but it's not wrong to call decibels intensity, even though they don't have units of intensity, because they do relate directly to it. They're an alternative scale, right? Okay, anyway, so 105, and that actually is quite loud, right? That'd be very, very noticeably loud, and you're only about 4.5 feet away. So let's find out though, if you decide you're going to go right up to that person, or maybe the person yelling goes right up to you, and they yell right in your ear, well, how close do they actually have to get until it becomes painful, right? Because it is possible for human yelling to actually hurt the ear, right? And one of those kind of given arbitrary thresholds for sound created pain is 130 decibels. Now you might think, oh, well, 130 is not much bigger than 105, but remember, this is a logarithmic scale. So to say that 130 is not that much bigger than 105 is actually wrong. It's over 100 times more energy per square area per time, okay? Because remember, it's powers of 10, okay? So let's go ahead then and find out this factor that's much stronger, okay? And I'll highlight that idea, by the way. We'll as our final kind of conceptual question, I'm going to finish by highlighting how to really think about decibels, okay? Ratios of decibels. So let's go ahead and just finish this problem though. Here we need to solve for R. So notice what I've done here. I've just set up the definition of decibels. I plugged in the fixed value that we're given. Our unknown here is R, and we need to solve for it. And the reason that R ended up inside the logarithm is I just replaced I with the definition of I as power over the surface area of a sphere. Okay, so then we just need to divide both sides by 10. This is just showing the algebra. Now I've got 13 equals log instead of 130 equals 10 log. Then I'm going to raise both powers, or both sides, to the power of 10. That's what I'm showing here. I'm not dividing by 10. I'm actually taking 10 to the 13th power and then 10 to the log power. Well, if you raise 10 to a log power, those two functions cancel each other out, and you're only left with the thing that was inside of the logarithm. So then we have 10 to the 13 equals, this which was inside the logarithm. So if I cross multiply by the threshold, then I get 10 to 13 times 10 to the negative 12. See? Okay. And now it's just a matter of more simple algebra, solving for that radius. And here we are, 8.9 centimeters. Okay. All right. So in other words, 0.089 meters. So that if they get right up the person, right close to your ear, then indeed the yelling at this high intensity of 1 watt would be painful. Okay. So there we have some practice with distances, calculating intensity with a given power, and so on. okay? And remember to get practice with how to work with your logarithms and how to undo them, for example here, raising both sides to the power of 10, okay? All right, so example 3, kind of similar idea here. Music is playing from a stereo and heard by a person at a distance of 2.5 meters at a loudness of 50 decibels, which is not all that loud actually. If the person moves to a distance of 13.5 meters and desires that the music appear just as loud as before, how much more power will the speaker need? Okay, so we'll start with the formula here, okay? And then I'm gonna do the same sort of thing I did in the previous example, replace I with the definition of power per the area, surface area of a sphere, okay? And then, okay, what I need to do here is then just go ahead and what we did see. So we want to solve for the power, okay? So we're gonna solve for P naught. We're gonna solve for the initial power. So P naught is just the power of the speaker when it's operating at its original distance. Okay, so that's all I'm doing here. Same idea, but instead of isolating R, I'm isolating P. All right, and notice I have this ratio of the decibel value divided by 10 because I've left it entirely symbolic. Okay, and now here I'll finally plug in my values, and here I get that dramatically small value, only 7.85 microwatts, right? So wow, I guess speakers are not very energy demanding, right? Okay, well, in this case, all right, and then let's go ahead and find the same idea. So I will use kind of this derived formula that I came up with here, right, which is power as a function of, well, as a function in this case of distance, but it could be a function of decibels as well, right, if you wanted to make this your known value and make beta your variable, all right? And so in this case, I'll plug in the greater distance, the greater radius of 13.5 meters, and then we get much more power, right, because it does take more power to make it just as loud at a much greater distance, right? And obviously it's proportional to the square, all right? So, all right, so there we go. And then our difference then is gonna be our 2.29 watts. So I guess that would be 0.2 milliwatts, or you could also think of this as 22.9, or well, let's see, because that would be actually 229 microwatts minus 7.85 microwatts. And this one's so small, it's hardly gonna affect the number, and we're left with 221. So if anything, that tells us that increasing the distance had a big effect, right? We had, if we took this as a ratio, we can see that it's about 50 times more power that the speaker needs to run on now to make the music just as loud at that greater distance. Okay? All right, so finally, let's finish off with a couple of concept questions. All right, 3 of them. So question 1, increasing the intensity of a sound by a factor of 2 will create what change in the decibels? So in other words, does doubling the intensity mean doubling the decibels? Well, certainly not, because the whole point of the decibels is the logarithmic scale. So doubling the intensity actually shouldn't have that big of an effect on the change in the decibel value. Let's see, okay? So the idea here, I want to do kind of a setup here. The change in decibels would be, some decibel, some new decibel with its new associated intensity minus the original decibel. I'll zoom in this a bit because it's so small. And the original associated intensity, right? So this delta B here would be B2 minus B1, where you can see this is the B2 value, this is the B1. So it's final minus initial, and these are just the definitions, okay? Now we're gonna work this together using the laws of logarithms to simplify it, because it simplifies very nicely, okay? So what we'll do then is we'll go ahead and take these 2 logs, okay? And we're going to take, first of all, division within the log is subtraction outside the log. And the reason we would do that is because once we do that and we consider that we distribute our negative here, then we're actually going to end up canceling out our threshold intensity. So in other words, finding a change in decibels, a delta B, is completely independent of the threshold intensity. It's actually a more general question. So that would apply to any perception, not just human perception, with that, again, kind of specific to humans, threshold intensity at 10 to the negative 12 watts per square meter. Okay, so that's kind of cool. All right, and then let's then take it back, right? So we've canceled out that term that had the I naught, okay? And then we're actually going to use the law of logarithm again to actually turn the subtraction outside the log into division within the log, okay? So in doing that, then look what we got. Now we see that a change in decibels is just equal to 10 times the log of the ratio of the intensities, right? The 2, right? So that's basically I final, which is I2, divided by I initial. It's kind of neat, right? It's just a testament to how subtraction and division is so directly related when you're dealing with logs and exponents, okay? All right, what are these powers of 10? Okay, so with that out of the way, we'll go ahead and use that formula and then say that a change in decibels for I equals 2I would just be equal to, well, it would just be 10 times log of 2I over I. Obviously, the i's cancel, so it would be 10 times log 2. What's 10 times log 2? It's 3.01. So it is not a big change. So doubling the intensity is just turning the decibels up by 3. And we saw a much bigger change, right? Think about the going from 105, which was loud, to 130, which was painfully loud, right? That was a difference of 27, right? So that would be many, many times over, doubling, right? So doubling is a factor of 3.01 decibels. Almost, you can round to the 3, okay? All right, cool. All right, question 2. Increasing the intensity of sound by a factor of 10 will create what change in decibels? Okay, so since it is based on 10, you might guess, okay? So let's see. So we'll increase by a factor of 10. So I'll have I2 equals 10, I1. Use the same formula. All right, so then it's going to be 10 log 10, which means it's a change of 10. All right, so a factor of 10 is a numerical increase of 10. Okay, all right. So does that mean that a numerical increase in decibels by 20 is a factor of 20? Right? Is it just, well, no, of course not. See? Yeah, then don't get caught in that trap. Because what would it be? It would be 100. Okay? What about if the numerical increase in decibels is 30, which it almost was in the previous problem when we went from 103 up to 130, right? 27 increase, that's almost 30. In that case, it wouldn't be a factor increase of 30, it'd be a factor increase of almost 1,000. Okay? So, in fact, let's do that. Let's do one with a 30 decibel increase. So what factor of intensity increase would be necessary to create a decibel change of 30 decibels? Okay, so here, instead of plugging in the intensity, we'll actually plug in the decibels, and then we'll go ahead and solve for the factor increase, which I call x. Okay, so then see, I just simplified thing, canceled out the fact that it's that it's one number is multiplied by the other. So obviously the numerator and decibels, or numerator and denominator, have a value that cancel, and then set this up, solve for x. Okay, almost there. So I get x to the 10 third power. See? So whatever that factor increase is the power of 10 of the intensity increase, the actual watts per square meter. So a 30 decibel increase in the loudness of sound is equivalent to a 1,000 factor increase in intensity. Okay? So what if you turn the decibels up by 40? Well, that would be, you guessed it, 10,000. Okay? Get the idea? All right. Well, good. I hope these ideas of working with the logarithms make sense, and a few of these relatively simple problems of calculating power and then potentially doing those decibels all work together well for you. And I hope this lecture was interesting and informative. Thank you so much for watching.